Now we're going to look at number patterns and sum formulas. We've already seen that 1 is equal to 1 squared. That's pretty obvious. 1 plus 3 equals 4, which is 2 squared. 1 plus 3 plus 5 is 9, which is 3 squared. And 1 plus 3 plus 5 plus 7, plus 7 equals 16, which is 4 squared. This pattern continues forever and can be proved by mathematical induction, a process by which we assume something is true for one case and show it to be true for the next. Any even counting number can be written in the form 2k, where k is a given counting number. Therefore, any odd counting number may be written 2k minus 1. For example, 5 is equal to 2 times 3 minus 1. Formally, the sum of the first n odd counting numbers is 1 plus 3 plus 5 plus a bunch of other stuff plus 2n minus 1, and that's equal to n squared, where n is any counting number. So this is what we call a sum formula. Now we're going to look at some additional equations and see if we can verify that they are true. We can see that these are true. We want to find the next equation in each of these lists and verify it is true. Take some time, pause the screen if you like. We'll talk about this in a few moments. Okay, continuing from here, in this first one, we have 1 squared equals 1 cubed, 1 plus 2 squared equals 1 cubed plus 2 cubed, 1 plus 2 plus 3 squared equals 1 cubed plus 2 cubed plus 3 cubed. In theory then, 1 plus 2 plus 3 plus 4 squared should be equal to 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. I said theory, she thought I said Siri. So if I take these numbers and add them together, that's 1 plus 2 plus 3 plus 4 is 10, which is 100. 10 squared is 100. So let's check this against 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. 1 cubed is 1, plus 2 cubed is 8, plus 3 cubed is 27, plus 4 cubed is 64. 1 plus 8 is 9. 27 plus 64 is 91, which is 100. So yes, we have verified that the fourth equation in this list is true. Now let's take a look at the fifth equation over here. We're saying that we've got 1 equals 1 cubed, which it does. 3 plus 5 equals 2 cubed. 7 plus 9 plus 11 equals 3 cubed. And 13 plus 15 plus 17 plus 19 equals 4 cubed. What this looks like is we are taking a set of n odd numbers and adding them up and getting n cubed. So we need to take the next 5 odd numbers. So that would be 21 plus 23 plus 25 plus 27 plus 29, and add those up and see if it's equal to 5 cubed. Well, 5 cubed is 125. So if these 5 numbers add to 125, we're in good shape. One of the nice things about this is that we can add these 2 numbers and these 2 numbers, and each of those is going to add to 50. And then we're left with that 25, so we add that there, and we get 50 plus 50 is 100, plus 25 is 125. Those are also equal. We have verified the next equation in each case. Last thing we want to talk about are some special sum formulas. For any counting number n, 1 plus 2 plus 3 plus a bunch of other stuff plus n, all squared, is equal to 1 cubed plus 2 cubed plus 3 cubed plus a bunch of other stuff plus n cubed. That's the one that we just verified, the first of the two patterns that we just verified. Also, 1 plus 2 plus 3 plus a bunch of other stuff plus n is equal to n times n plus 1 over, I wrote that number wrong, that should be over 2, not over n. There we go. So we can prove this second equation by deduction. Let's let S be the sum 1 plus 2 plus 3 plus all this other stuff plus n, adding up all of the counting numbers from 1 to n. We can also write that as n plus n minus 1 plus n minus 2 plus everything going down to 1, because this is just, we would have 1 and 2 and 3, because this would be n minus n minus 1, sorry, n minus n minus 1, n minus n minus 2, and so on. So when we add these together, we can set this up so we have, here is our first representation for S, and here is our second representation for S. And if we add them together, on the left, of course, we have 2S, but each of these things adds to n plus 1. N plus 1 is certainly n plus 1. N minus 1 plus 2, that's n plus 2 minus 1 is n plus 1, and so on. And note, there are n terms in each of these sums. We know that this has to be n terms, 1, 2, 3, and so on up to n. This has to be n sums, n, n minus 1, n minus 2, and so on down to 1. That's n terms. And so this has to be n terms as well. So that's n times n minus 1. So 2s equals n times n minus 1. Then if we divide both sides of this by 2, we get s equals n times n plus 1 over 2. It's also worth noting that 1 plus 2 plus 3 plus all of this stuff up to n gives the nth triangular number. So this n times n plus 1 over 2 is the nth triangular number.